Welcome to the lesson 7 of industrial instrumentation. In this lesson basically we will discuss the thermistor. As you know, the thermistor is a temperature sensitive device. I mean, if you increase the temperature, its resistance decreases, and by using this property mainly it is used as a temperature sensor, but it has many other applications in electronic circuits that we will discuss one by one. Now, contents of this lesson is its resistance temperature relationship or characteristics, composition of a thermistor, because it is a semiconductor material. So, you have to look at what are the compositions and how it is made, manufacturing process, how actually thermistor is made, and thermistor in a Wheatstone bridge. This is very important. We will show that Wheatstone bridge is used to take an unbalanced voltage which is calibrated in terms of temperature, and its linearity of operations. We will also see the thermistors in a potentiometer circuit. Either you can use it in a Wheatstone bridge or in a potentiometer circuit. We will see both, we will analyze both. And what is the linearity of operation? Thermistor is a very non-linear sensor. So, we will look at all these things. At the end of this lesson, the viewer will know thermistor, all its characteristics, it is used in the how it is used in the electronic circuit, what are the signal conditioning circuitry associated with the thermistor, along with its applications as a temperature measuring element. These are the main applications, but we will touch some of the applications, even though it is not within the purview of the industrial instrumentation, like in the power supply circuits, in the Wien bridge oscillator circuits. There are some uses of thermistor in those applications also. As I said, other applications of thermistor. Now, a thermistor, it is a temperature sensitive resistors. As you know, all the resistors are temperature sensitive. If you increase the normally, if you increase the temperature, resistance increases. However, unlike metals, it shows a decrease in resistance value with the increase in temperature. These are the unique features which we have in the thermistor, which no other resistors have this type of property. Okay, this is inverse. I mean, its resistance is not increasing with the increase of temperature, resistance decreases with the increase of temperature. Rather, I should if I draw it, it will look like the characteristics will look like this. You see that, suppose if I draw here, temperature here and resistance here, the relationship is exponential like this one. Clear? This is the temperature versus resistance relationship of a thermistor. It is made of oxides of nickel, cobalt or manganese, and sulfides of iron, aluminum or copper. The resistance temperature relationship can be expressed as R equal to R naught exponential to the power 1 by T minus 1 by T naught. What are those legends? R equal to the resistance of the thermistor at T Kelvin, R 0 is the resistance of the thermistor at T naught Kelvin, and beta is the material constant that ranges from 3000 to 5000 Kelvin. In fact, actually I am sorry, there is a mistake. So, it will be beta multiplied by this. So, beta multiplied by 1 by T minus 1 by T naught. This is the thermistor, because this is unitless quantity, that should be. So, beta is a material constant that ranges from 3000 to 5000 Kelvin. Now, one thing is very interesting, you see that as the value of beta, always we desire that the value of beta is, it is not very difficult to find the value of beta, because I can measure the temperature, I can measure the resistance at two known temperature. So, obviously, from that I can find the value of beta. Now, as the beta is higher, always people prefer to beta should be higher. The reason is that if the beta is higher, you will see that if the beta is higher, the relationship will be sharper and sharper. That means beta increases this direction. Beta increases in this direction. As you can see, if the beta increases, sensitivity, that means this temperature versus resistance relationship, sensitivity of the thermistor also increases. That means, for the same rise of temperatures, I will get higher decrease of resistance. So, that is always an advantage for making any instrument, that the instrument should be more and more sensitive. Clear? I should go back. As I told you, this should be beta should be multiplied, right. The sensitivity S of a thermistor is given by S equal to delta R by R by delta T. If you can derive, then I will get minus beta by T square. If beta, for an example, if beta is equal to 4000 Kelvin and T is 298 Kelvin, S will find the S value of S will be equal to minus 0.045 per Kelvin, and this is much higher than the sensitivity of platinum RTD. Platinum RTD is not that this sensitive, because both are resistive sensors. As you know, RTD means is basically a resistance temperature detector, and I mean, if you look at the sensitivity of the RTD is much higher. So, it helps to measure the very small difference of temperature. Now, manufacturing process, if you look at, the two or more semiconductor powder are mixed with a binder to form a slurry. Small drops of the slurry are formed over the lead wires, dried and put in a sintering furnace. During sintering, the metallic oxides shrunk onto the lead wires and form the electrical connection. The beads are then sealed by coating it by glass. It looks like this actually. So, two wires will take, I should draw it here. I should draw it here. So, two wires are there which is coming out. So, these slurries are dropped on this one. Okay. Now, it put on a sintering furnace. So, I will get a bead like this one, right. So, what will happen? So, this will, sorry, this again. I will draw it here. Okay, let me erase first. So, I can slurries are dropped on this one. So, it is put on a sintering furnace. Now, if you put in a sintering furnace, what will happen? You know, it will shrink, and this shrinking process will make the very good electrical connections. Now, please note that the thermistors are very sensitive to the, since it is a semiconductor device, it is sensitive to moisture also. So, there should be some protection, so that it will not deteriorate with the moisture, performance totally deteriorate with the moisture, right. The glass coating improves the stability by eliminating the water absorption. So, obviously, if you make a glass coating, so water cannot be absorbed there. The typical size of a thermistor, it is 0.125 millimeter to 1.5 millimeter. As in usually we compare the three basic temperature sensor, one is thermocouple, then RTD, then thermistor. you will find that the thermistor has the smallest size. I mean, some of the size is so small, it is sometimes very difficult to even look at the naked eye. It can be made so small. Now, making this small, there are two advantages of making such a small size. Even though you have to put on glass coating and all these things, first of all, its time constant of the thermistor is very small. If you compare to thermocouple and RTD, time constant of the thermistor is very small. That is a great advantage. And making it this small size also will allow you to measure a temperature in a very narrow location, very small location where there no other sensor can go inside, right. Shape, it has a various shape, it can be available in disc, wafers, flakes as well as in rods. These are the different shape of the thermistor. And resistance of the thermistor may vary from few ohms to several kilo ohms. Usually, as you know, the thermistor, one application, as I told you, that you will find that it has in electronic circuits also we use it. Now, resistance of the thermistor may vary from the few ohms to several kilo ohms. Now, one thing you should very careful about the minimum resistance, because as the temperature increases, its resistance drops, its resistance falls. So, it should not fall in such a way that it will make either it will draw a huge current from the voltage source, from a battery. That means prevention of short circuit should be there, and also it should not load the subsequent instrument, because if you have the very low resistance, obviously there is a chance of loading the subsequent signal conditioning circuit, that is to be also avoided. Other semiconductor conductor temperature sensors include the carbon resistors, silicon and germanium. These are some other sensors, even though which are not much in use. Now, silicon with varying amount of boron impurities can have either positive or negative temperature coefficient of resistance. So, you can have either positive thermistor or a negative thermistor. We are not interested to have a positive temperature coefficient, because we have many other sensors, but we need negative temperature coefficient, that also with a very high sensitivity, it is available in the case of thermistor. Now, germanium doped with arsenic gallium is used for cryogenic temperature when it shows a large decrease in resistance with increase of temperature, because as you know, cryogenic instrumentation is one of the very important instrumentation, especially the measurement of temperature of the liquid helium and all those things. You will find that in such a cases, because many a times it is necessary to measure all this superconducting circuitry and all these things, you have to should measure the temperature. So, the cryogenic temperature measurements is again another challenge. So, in that type of situations I can apply the thermistors, and it is germanium doped with arsenic gallium, and it is used for cryogenic temperature, where it shows a large decrease in resistance with the increase of temperature. Now, applications in electronic circuits, it limits the large charging current for power supply filtering capacitor, that will show later on at the end of the lesson, that how it can be controlled. It has also applications of stabilizing the Wien-Bridge oscillator circuit. It is also used for stabilizing our Q point stability of our analog amplifier circuits, transistorized amplifier circuit. So, all these applications will show later on. Now, please note that in the case of thermistor, if I take a white page, it is actually available, those are, because there are two types. Is resistance is drawn like this one, and in electronic circuits when they are using making a dot like this one. This is the case of thermistors having dots, which is used in a electronic circuit. In that type of cases, it is available in the form like this one, disc like. So, two wires are coming out and it is color coded. So, that means it is happen, you see that it looks like this. So, color code is put here, so that people will know what is at the room temperatures or at some particular calibrated temperature, what should be the resistance of the thermistor. Right, resistance is not very constant, as you know, that because it is sensitive. Even though in the case of suppose a carbon resistors, when you buy a carbon resistors, there is a color code on the carbon resistors. So, obviously, that color code, I mean that value depends, I mean value actually referred to some particular room temperatures. Whereas, in the case of thermistor, that temperature is very important, okay, because it is varying a large, it will vary large at the increase of temperature. So, color code is there. Whereas, in the case of thermistors, which is used in as a sensor, you will find it is like this one on a glass. So, it is glass coating. So, they put a thermistor there, right, and wire is coming out, right. If I go back, now thermistor can be used as an active element in Wheatstone bridge, because you know it is a resistance change. Ultimately, the if I want to measure at any temperature, so what will happen that you have to calibrate the output voltage in terms of temperature. If you use the bridge as an unbalanced, I mean if you use the bridge in an unbalanced condition. So, I have to make the that unbalanced voltage should be calibrated in terms of temperature. That is actually done in the case of if you use it as a temperature measuring device. There are various, I mean you can use a voltage to frequency converter, and frequency can be calibrated in terms of temperature. There are various means, people tried with so many alternative. They have tried also with an thermistor as a frequency changing elements of the circuits. Otherwise, as you know, very standard features that the unbalanced voltage of the Wheatstone bridge can be given to a V2F converter. So, that the frequency will be directly calibrated, can be directly calibrated, which can be measured by some frequency measuring devices, and that can be calibrated in terms of some frequency measuring circuit. That frequency can be calibrated in terms of temperature. That is also possible. By all this means, actually people are doing all these different, I mean methods just to increase the resolution, to increase the sensitivity, even though it is a quite sensitive devices. But in some situations where the fraction of the temperature change of measurement is important, in that case we have to think of that type of change of frequency with the increase of temperatures and all those things. Now, this is a Wheatstone bridge we have seen, you can see this one. You see here, this is a thermistor. So, I can put a dot here. If I choose a yellow pen, so I can put a dot here. So, it is thermistor, others are just simple carbon resistors. These are bridge excitations E subscript X, and this is our output voltage. Now, if the initially the bridge is balanced, then what will happen? Suppose all RT, R2, R3, R4 all are same, all are same, then bridge will be obviously balanced at room temperature suppose. Now, suppose there is a temperature change in RT. So, obviously, the resistance value of the RT will change. Okay. So, if the resistance value of the RT decreases, I will get an unbalanced voltage. Previously, unbalanced voltage is 0. Now, I will get some unbalanced voltage. That unbalanced voltage can be calibrated in terms of resistance change, and that resistance change unbalanced voltage also further can be calibrated in terms of temperature. This unbalanced voltage I can feed to a V2F converter, and this a frequency measuring circuit, a counter or frequency measuring circuit, right. What it will do? So, it will simply do, it will measure the frequency, and the frequency will be calibrated in terms of temperature degree centigrade. The advantage of this type of thing is, as I told you earlier, the resolution sensitivity also can be increased, because I have a signal conditioning circuitry where I can make all this type of manipulations, so that I will get the frequency change more sensitive. Now, if the Wheatstone bridge is initially balanced, we assume that the Wheatstone bridge is initially balanced, even not necessarily that all the resistance will be equal. If this condition values that RT into R3 equal to R2 into R4, then what will happen is, you can see, if R2, R3, R4 are fixed value resistors, then the output voltage E naught due to change in resistance delta RT for change in temperature will be derived as follows. Okay. If we redraw, let us redraw the Wheatstone bridge again. So, we will find, so we have redrawn the circuits, we have labeled something A, B, C, D. We have taken in clockwise direction, this is RT thermistor, then R2 carbon resistors, R3 fixed resistors. So, I should rather say that these resistors R2, R3, R4 is temperature independent. That means, if the temperature varies, this resistance, their resistance do not change. Fine, we can accept that thing. Now, EAB, you can simply see that it will be equal to RT upon RT plus R2 multiplied by EEX, because this is our excitation, is not it? This is our excitation voltage. Then EAD will be equal to R4 upon R3 plus R4 multiplied by EEX, where EX is the excitation, right. Now, the output voltage E naught equal to EBD equal to EAB minus EAD equal to RT upon RT plus R2 minus R4 upon R3 plus R4 multiplied by EEX, right. So, again it is now, so this is our E naught, so this is our E naught equal to this voltage, fine, no problem. Due to change in temperature, the new value of the resistance is RT, is no more RT. So, it is RT plus delta RT. Whether delta will be positive, negative, that I am not thinking, that I will discuss later on. There is a change, and we say that the RT plus it is delta RT. If it is there, then you see that I can write that E naught new value of RT, let me take this one, RT plus delta RT, because it is a new value of RT. Okay. What is this new value? This is due to temperature change, RT is replaced by RT plus delta RT in these equations. So, RT plus delta RT R2 R4 upon R3 plus R4 multiplied by the excitation EX. If I make all these cross multiplications, I will get, in the denominator I will get the RT plus delta RT R2 R3 plus R4, numerator I will get RT R3 plus delta RT R3 plus RT R4 plus R4 delta RT minus R4 RT minus R4 delta RT minus R2 R4. Now, interestingly you see that what will happen, that here these will cancel out obviously, if I take out it will be easier. You see that this and this will cancel out, RT R4, this and this will cancel out, is not it. Then R4 delta RT and R4 delta RT also will cancel out. Now, RT R3 according to the conditions, this and this will cancel out, is not it. So, if I look at, so what will remain? Will remain delta RT into R3. So, this is the only factor which will remain in the numerator upon RT plus delta RT plus R2 multiplied by R3 plus R4, right, because the condition is RT R3 equal to R2 R4, that is the reason the first term and the last term was cancelled out. So, ultimately I will get the expressions E naught upon excitation EX will be delta RT into R3, RT plus delta RT plus R2 whole multiplied by R3 plus R4. Now, assume that if R2 equal to R3 and RT equal to R4, the equation 1 becomes, you see RT delta RT by RT, I mean upon 1 plus delta RT by RT plus R2 by RT 1 plus RT by R2. If you just in the numerator it will remain same, it will remain same in the numerator. So, in the denominator if I multiply, a 2 will come, because you see here this R2 RT and RT R2 if you multiply you will get another one. So, this will make 2, then RT plus by R2, R2 by RT plus delta RT by RT plus delta RT by R2, this is equation number 2, right. So, finally, I will get an equation for the thermistor you see the interesting thing is that in the last equation, equation number 2, that the terms delta T by R T and delta T by R 2 is in the denominator are not small enough with respect to the other term. Therefore, they cannot be neglected to simplify the solution of the equation for delta T by R T. For special case of an equal bridge R T equal to R 2 equal to R 3 equal to R 4, rearranging equation 2 we get E naught by E x equal to delta R T by R T upon 2 plus R T by R 2 by R T plus delta R T by R T delta R T by R 2. If we do these things, so ultimately I will get, because if the R T equal to R 2 we have assumed already. So, I will get an expression, we have assumed that the R 2 equal to R 3 and R T equal to R 4. So, I will get an expression which looks like, we have assumed R 2 R T R 2 R 3 R 4 are all same. So, I will get an expression like this one. So, this will lead to delta R T by R T 4 plus 2 multiplied by delta R T by R T, right. So, if I make a little algebraic manipulation, so this will be, actually this will be minus sign, bigger minus sign should be there, 4 E naught by E x 2 delta R T by R T minus E naught by E x equal to delta R T by R T, right. So, delta R T by R 2 1 minus 2 E naught by E x equal to 4 E naught by E x. So, delta R T by R T equal to 4 E naught by E x 1 minus 2 E naught by E x, equation 3. Now, the thermistor resistance R T at any temperature T is then given by the simple expression, actually this is wrong, mistyped. So, this will be equal, right, this will be equal sign, that means R T dash equal to R T plus delta R T, right. So, I can write that if I take R T common, so R T 1 plus delta R T by R T. So, this is equation number 4, substitute equation 3 in equation 4 we get R T dash equal to R T 1 plus 2 E naught by E x 1 minus 2 E naught by E x, this is equation number 5, right. And the value of R T obtained from the equation 5 is converted to a temperature by using tables that list as a function of R T for the specific thermistor being used, right. So, we will get a table, so we can find it, we can make a calibrated, and as you know ROM, and we can make a calibrated ROM for also this type of purpose. So, the ROM advantage is that all those linearity problem, non-linearity problem can be easily eliminated in the case of thermistor. Okay. Even though it is a excellent devices, very sensitive, very small in size, I mean it can be used for the dynamic temperature measurement, everything is there, but the problem is that non-linearity. Even though thermocouple is also non-linear, but the advantage of the thermocouple for a short range you can consider as a linear sensor, I am sorry. Now, thermistor also can be used in a potentiometer circuit, right. You see there are various potentiometer circuit used in the potentiometer circuit as follows. You see this is one of the thermistors which is used in a potentiometer circuit, right. You see here that this should be the sign. So, this is the thermistor R T and R 1. In this case, if R T equal to R 1, so R T dash will be equal to R T, that means change resistance, where R T dash as I told you earlier equal to R T plus delta R T. R T dash equal to R T 1 minus 2 E naught by E x excitation upon 1 plus 2 E naught by E x. Now, interestingly, one common question arises, what will happen if I flip it? That means, if I put R T here and R 1 here. That means, the circuit, if the circuit looks like this, then what will happen? If I take a white page, that means suppose I have an excitation. Okay, let me take first erase this one. That means, if I take a, that means actually our circuit we got that like this one, is not it? Thermistor here, RT we have connected here, this excitation Ex, I am connecting this output voltage, this is R1, right. Instead what will happen, if I make the circuit like this one, R1, I will put the thermistor here. You remember in the previous some time back, we have discussed the instrumentation engineers must consider the loading effect or the thermistor in case of temperature. Why it is not used? You see, like this one, is not it? Here. Now, what will happen if the temperature rises? If the temperature rises, you see the thing will happen, this resistance will fall and fall, right. So, the impedance of this resistance of the impedance from looking from this side will be different, right. In some cases it will some value, in some other cases. So, it will make the problem in the subsequent signal conditioning circuit. That means, if you have a signal conditioning circuitry here, so that designing that type of circuit will be different. Whereas, if you make the circuit like this one, you see the I will get some impedance R1 always same, right. So, that is the reason instead of connecting like that, I put the thermistor here. So, this circuit should not be used. So, we should use this circuit. What will happen if the temperature changes, this resistance will fall and we will get more current through this resistance which is in series, and I will take the output voltage. So, obviously, output voltage also will increase, because if the current is I1 suppose. So, I will take the current E naught equal to I1 by R1. If R1 increases, R1 decreases obviously, sorry, if the I1 increases, because if the resistance falls, obviously I1 will increase, this value will value of the voltage will increase. So, as the temperature increases, the E naught will increase, right, because this current will increase, because this has fallen down, right. So, that is the reason we have got the expression RT dash equal to RT 1 minus 2 E naught upon Ex, excitation 1 plus 2 E naught by Ex, right. This is one of the circuit. Some other circuits to improve the linearity of operations are as follows. You see some of the circuits we have shown. These are various circuits to influence the impedance, output impedance and all those things. These are the circuits we will discuss. This is a thermistor here. Instead of they are put in a circle, instead of putting a dot, they have put a circle like this one, and this is another circuit. So far the thermistor, as if increase the temperatures, sensing devices, we have seen that we can also prove analytically that whether you use it in a bridge or in a potentiometer, its sensitivity resolution does not vary much, okay, it does not vary at all. But however, you will find that if you use a sensor like this one, if you use suppose a circuit like this one, I will get always some advantages. I will show you what is the advantages. These are another circuits of the thermistor which is used in a bridge circuit. You see here, there is typical reason why we have connected a resistance in parallel with the thermistor. Now, as I told you, thermistor are nonlinear devices. So, linearity is a great problem with the thermistor. So, what they are doing, they always, this is a common thumb rule that you use a resistance in parallel with the thermistor, right. So, what will happen, you see. So, I have a thermistor, any circuit, we have seen two circuits, one is a circuit like this one, right. So, this is a thermistor and like this one we have seen, right. I can take the output voltage from this position, or we have seen a bridge circuit. Excuse me. So, we put a bridge, we put a resistors here, right. So, this is RT. So, I put a resistors in parallel. This is R2, R3, R4, clear. Now, any resistance, if I take a new page, whenever you are connecting a resistance to a thermistor, you know what will in parallel to thermistor, you know what will happen with characteristics. Suppose I have a characteristics like this one, temperature versus resistance characteristics of a thermistor, it looks like this. Okay. Depends on the value of beta, how sharp it will come down. Okay. As I told you in the beginnings, that the higher the value of beta, sharper and sharper will be the fall, that more and more will be the sensitivity of the thermistor. Always we want the sensitivity should be more. Now, if you connect a resistor in parallel with the thermistor, you will lose first of all sensitivity, and if you lose the sensitivity, it will look like this one, you see, it will look like. For some small range, I can use that thermistor almost as a linear devices. If I use a thermistor with resistance in parallel. So, it won't be a fully linear, it is not possible, because it is already a nonlinear devices. Okay. So, it is exponential fall, but if you use a resistance in parallel for a small range, it will become linear. So, by sacrificing the sensitivity, I am making the circuit or thermistor linear. This is my circuit as we discussed. Now, when thermistors are used to measure the temperature, the errors resulting from the lead wedge effect are usually small enough to be neglected even for a relatively long lead wedge. Now, this is the typical problem of any temperature sensitive devices. When you are making a temperature sensitive sensor, this is a typical problem, because the resistance of the lead wedge, because you see that you cannot put suppose I have a, you cannot put like this one, that means suppose I have a, what I am saying, suppose I have a furnace here. Okay. You cannot put a thermistor might be inside, you cannot put the you cannot put inside the very near to this meter. So, you have to take out, suppose I have a furnace here. So, you have to take out the wires, and might be here we have the meter. Okay. Here I have the sensor, suppose these sensors inside. So, this is the lead wedge. It can be few meters also, right. It can be few meters, it is all temperature measuring, whether it is thermocouple thermistor and or RTD, it does not matter. So, this lead wire creates the problem. Now, actually lead wires is not very critical in the case of thermistor, because of the reason that the thermistor resistance value is quite high compared to the lead wire resistance, because there are many problems. Suppose there is a temperature change along the lead wire. So, obviously, your total resistance, because if you look at the meter from this side, what it will see? It will see that the total resistance, it will not care, it will not see only the thermistor resistance, it will also look at the lead wire resistance plus thermistor resistance. So, the lead wire temperature variation is very important in instrumentation, right. So, it is not important in the case of thermistor because of its typical value, its value is high, but it is very important in the case of RTD. We will see that in the later lesson, right. And even though for a, so you will see that when the thermistors are used to measure the temperature, errors resulting from the lead wedge effect are usually small enough to be neglected even for relatively long lead wires, can be few meters also lead wires. The sensitivity of a thermistor is high, therefore, the change in resistance delta T resulting from a temperature change is much greater than the small change in resistance of the lead wires due to the temperature variation. This is very important, right. That is the reason we can have a long lead wires in the case of thermistor. Also, the resistance of the thermistor is large compared to lead wires resistance, which already I discussed these things, can be reached typically can be RT by RL can be 1000. Consequently, any reduction in sensitivity of the sensor due to the lead wire resistance is negligible, right. Now, there is another problem with the thermistor, it is called self-heating error. Any resistance devices, whenever you are using the self-heating error, it is common to both the thermistor as well as RTD, right. This cannot be avoided. This is a physical phenomena, you can avoid the lead wire problem, okay, but you cannot avoid the self-heating error. Errors may occur due to the self-heating of the thermistor. Recommended practice is to limit the current flow through the thermistor to a value such that the temperature rise due to the I square RT power dissipation is smaller than the precision to which the temperature is to be measured. Okay. So, actually the precision will tell you how much current you will pass through the thermistor, right. So, sensitivity and precision, if you look at very careful, that is going side by side. So, let us look at. Now, suppose that RT, that means resistance of a thermistor, is 5 kilo ohm, is capable of dissipating a power of 1 milliwatt per degree centigrade above the ambient temperature, right. So, thus if the temperature is to be determined with an accuracy of 0.5 degree centigrade, the power to be dissipated should be limited to less than 0.5 milliwatt, right. This limitation establishes a maximum value of the current. What is that maximum value? We will show this. So, you see that the maximum value of current which will pass through the thermistor can be P by RT equal to 316 microampere. This will actually lead you to choose your bridge excitation or the potentiometer value, value of the potentiometer excitation or the value of the Wheatstone bridge excitation, right, because you can calculate how much the maximum current will be allowed and accordingly. But please remember, if you do that thing, obviously you will lose the overall sensitivity of the system, because your output voltage also will be getting reduced, is not it. We are not measuring the resistance there, we are measuring the output voltage. So, output voltage will be reduced. So, adequate response can be obtained even at these low currents, because the sensitivity is high. So, sensitivity is high, I can make the adequate response, but this is a typical problem that sensitivity, that is advantage, because but obviously what will happen if you reduce, if you think of this in limitations, obviously you have to sacrifice some amount of sensitivity, that is quite obvious, that you cannot avoid. And I am sorry, it is not, thank you. So, let me go look at some of the circuits for which thermistor is used. As you know, the wind bridge circuits is a typical circuit, looks like this. You see the wind bridge circuit looks like this. Very familiar, it is a standard circuit for making commercial oscillators, okay. So, basically wind bridge oscillators. Now, there is R3, R4 like this one. So, these two voltage are coming to the an op amp. I will show you some of the other applications of the thermistor. This is the wind bridge oscillator circuit, right. These wind bridge oscillators. Now, see that always we will try to make the gain of this amplifier very high to oscillate. We will always make this gain of the amplifier quite high. Now, there are some resistance, suppose this is R, this should be R, if it is C, this should be also C. There is no doubt about that thing, and the frequency of oscillations omega naught will be equal to 1 by R C, right. Now, there are two resistance you see R 3 and R 4. Now, I am not going to details of this wind bridge oscillator, but you see that for stability of the system, the gain should not be that high that it should saturate the amplifier, it should not be that low also that your oscillation may not start. So, what they do commercially, they use either previously they use R 4 as a tungsten filament lamp, because as you know the tungsten filament lamp its resistance depends on the temperature. So, as the current as the time goes on its resistance increases, or you can use R 3 as a thermistor. If you use R 3 as a thermistor, what will happen as the time goes by, the current will start to pass through this one and its resistance value will decrease. So, that will control the amount of feedback you are giving to this oscillator. So, instead of tungsten lamp, I can use this type of thermistor for making a temperature, for making stabilizations of the wind bridge oscillator. This is one applications. In other applications, as you know that we make usually that our power supply, is not it. So, typically power supply looks like this, all instrument needs the power supply. Right. So, I am giving a supply here, right. This is our AC supply. After stepping down and all this is a full wave rectifier. So, I am getting a DC here, positive this side, negative this side, this is AC this side. Now, any full wave rectification, as we know that you see that our is not a DC, it is a full wave. So, I must smoothen it, because the pure DC should have a, suppose this is the time and this is the amplitude. So, this is the battery voltage E. So, it should be like this one, right. Now, what they do commercially, they put a capacitor, a large value of capacitors, right. Now, even for a suppose 1 ampere power supply, 1 ampere suppose 25 volt power supply. So, this around suppose 2500 microfarad or 3000 microfarad. This is a typical value for the power supply, okay. According to the voltage, whatever the voltage across the voltage, suppose if it is plus minus 25 volt power supply, I will choose a 50 volt power supply like this one, right. Now, the problem arises, you see that when you switch on, now what will happen here? You see, if I look at now what will happen, you see the now my output voltage, suppose this is output voltage, right. Output voltage will look like a slight fall, then again it will rise like this one, right, fall, because before the capacitor fully discharges, I mean charges, again it will fall like this one. The output voltage will charging and discharging of the capacitor, it will look like this one, almost steady DC voltage. The best filter for this power line filter is a pi section filter. That means you use a like this one, right. But L is not no more used because L has a lot of problems, associated problems, magnetic field, and it is costly, it is bulky. So, to avoid that, people use a simple capacitors of higher and higher value. So, in this case, suppose if you use a 1000 microfarad capacitor, 1000 microfarad capacitor, okay, then we should have a one, suppose this is a 0.1 or Henry or like this one. So, this will give you a very good, but this is not used, you use a very high value of the capacitance 2500 microfarad or 3000 microfarad capacitor value. Now, in this case, you know what will happen, you see that initially when you switch on the system, you will find there is a large current is necessary to charge this capacitor, because you cannot connect the capacitor like this one. There should be some bleeding resistors and all these things here, high value bleeding resistors. So, this is always necessary, because otherwise capacitor will be fully charged, right. So, what the people do, you know, because what will happen that if I charge this capacitor with a large current, because if it is totally discharge capacitors, it needs a large current, then what will happen, this there is a large surge current to the diode. So, diode will burn out, right. To limit this, what we have to do, what we can do actually, we can put a small value of thermistor in this position, right. If I take a new page, it will look like this one. So, I will put diode as before, okay. So, now put a capacitor there, small value of the thermistor, I have an AC. Now, initially what they do, you see it will offer high resistance, this thermistor, and capacitor will charge, and capacitor will slowly charge, because at this time what will happen that since it is high resistance, it will not charge fully. Then after some time what will happen, you see that as the time goes on, this its resistance is, as the temperature goes, because the current will pass, there will be self heating. So, what will happen to this resistance? Its value decreases, that I want actually, because it is a wastage, it is a loss of power, this will never be utilized. So, the efficiency of your power supply will be deteriorated, just to protect 4 diodes, because a semiconductor device, you can say, sir, I will use some fuse here. A semiconductor device is to be protected by another semiconductor device, please note that, right. So, you cannot do that thing. So, I have to use, so if I use this one, so it will offer a large resistance. So, slowly it will start to charge, and as the time goes by, this temperature resistance will increase, resistance will decrease, sorry, temperature as the current passes, resistance will decrease, because the temperature is rising, and I will get full, the loss within this thermistor also will be reduced, because there is no utility of, because this is a total loss, because this voltage will be. So, these are the typical circuits also used in SMPS also, because in SMPS also, you know, the switch mode power supply, for regulated power supply, for all that, for giving the power to all the chips also, they need some power supply, even though there is a switch mode supply, but for that reason they use a small series regulator. So, in those series regulator, I have a big diode rectifier like this one, and it will utilize the thermistor. Thermistor is also used in the electronic circuits also for, for stabilization. You know, the Q point stability is very important in the devices. Now, once you switch on, especially the circuit where there is a feedback, there is a chance of oscillation. So, what they do, they purposefully put a thermistor there, and this will limit the current, and this is a typical circuit I can show you. You see here, I have a you see this current is going There is a push pull circuit which is utilized for making amplifiers. Okay. Right. So, I am taking a load from this position, okay, and output. So, I am giving a power supply of 25 volt here suppose. Now, what they do actually, so I have subsequent circuits like this one. So, there is a DC circuit. So, this circuit is coming here, this circuit is coming to the collector. Like this one. Like this one. See, this is used as a thermistor, right. So, this can we do like this one. So, there is some resistance we can come here also through a capacitor. So, this 25 volt can be connected here. So, in fact, this is a 25 volt should come here. So, 25 volt, sorry, 25 volt should come here. Okay. So, this signal is, this is a typically a amplifier. So, where the signal will come here in this from these directions, right, it will go down there. Now, see the reason for there is also here connection here. The reason for this type of circuits is that this Q point stability, right. So, I need a stability of the thermistor. This is another application of the thermistors in the electronic circuits, right. So, it will make the Q point stable because due to the resistance and all these things it may happen that it will go out. So, because there is a feedback there. So, actually there is a feedback. So, it should go like this one and it should go. So, initially, so that may go to the oscillatory region. So, to stabilize these things, we use a thermistor, and this ends the lesson 7 of industrial instrumentation.